Right, so ladies and gentlemen, dear colleagues, welcome. My name is Daniel Gonzalez, and you are watching the 63rd talk of the scheduling seminar. Today, I am happy to introduce Defeng Sun. He is from Data Analytics and Optimization Group for Smart Industry uh, from Northeastern University in China. He made his PhD in 2016 at the same university with Lixin Tang on scheduling in a container terminal. Then he visited University of California at Berkeley, and he worked with Max Shin. And since some time, he's associate professor at Northeastern University, mainly interested in logistics scheduling in manufacturing industry and terminals. A part of that, he likes to play basketball, football, and skiing because he's relatively on the north part of China. So Defeng, it is great to have you here, and the floor is yours.
Okay. Thank you, Dinek. Hello, everyone. It's my honor to share my topic. I'm Defeng Sun from DAO Lab, Northeastern University, China. Today, I'm going to focus on a specific problem called Quay Crane Scheduling Problem. And then the methodology is Benders approach. So this is a joint work with Professor Li Xintang and Roberto Bortolacci. I'm going to first introducing the background. So let's see the definition. Okay, let me see. So we have to schedule the Quay cranes to unload or load the container from the vessels in container terminals. So actually, our aim is to minimize the maximum completion time so the vessels can leave on time and the efficiency of the terminals can be improved. So in this problem, then you see that all the Quay cranes, they are moored on the same trail. So when they operate the unloading and downloading of the containers, they have to avoid the collisions among the cranes. So the difficulties, sorry. So the difficulty is that the first difficulty is that we have to consider the spatial constraints. And the second is that there is a task precedence relationship between the tasks in the same bay. You can see from the right figure. So this is the two difficulties that make the problem very hard to solve. So for the best exact algorithm nowadays, we see that even the problems instance with 2 Quay cranes and 10 bays, the solution times will be up to 2 hours. So in this talk, we focus on to develop an efficient exact algorithm to solve this problem. So due to the difficulty of solving this problem in academia and the industry, we tend to use two approximate strategies to solve the problem called unidirectional schedule strategy and bidirectional schedule strategy. The first one is that we force the Quay cranes to move unidirectional only, from left to right of the vessel or from the right to left. So a lot of literature study these strategies. In 2024, we proposed another strategy to solve the same problem. It's called bidirectional schedule. In this strategy, we allow the Quay cranes to move at 2 directions. You can move first from left to right and then from right to left. And we found that this will lead to a better mixed bands. So you can see from this figure, the commission time is about 10 time periods better than the unidirectional strategy. So actually the advantages of these two strategies is that the first that assignment determines the sequence. You know that the key cranes, their moving direction have been fixed from left to right or from right to left. So when we determine the which key crane to for the one task, then the operating sequence is determined. So this will greatly reduce the problem complexity. So also for the precedence between tasks, we have concise precedence constraints. So that these the corresponding formulation can be solving firstly by the state-of-art solving software like C++, and we can actually we can obtain really good solutions, near optimal solutions. But the disadvantage is that we lose optimality, and some variants of Quay Crane Scheduling Problem cannot be handled by these two, the aforementioned two strategies. You can see that these the Quay Crane Scheduling Problem at indented berths, like you see that there is two berths on the both sides of the vessel. Then the Quay Crane like the collision relationship between the Quay cranes are really different from the previous general problem. Like in this problem, there are only one berth on the one side of the vessel. So actually, our contribution is that we propose a new compact formulation for the problem, and can be used to solve a lot of the Quay Crane scheduling variants. So we also work on the combinatorial benders approach, which is capable to optimally solve the medium-sized benchmark instances. So the approach is based on the various valid inequalities and several types of combinatorial cards. So let me first introduce the variables. So the first group of variables is about task, the assignment and the sequencing. So you can see that we have one y variable. That means that you can assign a key crane to each task. And the second x variable indicates that the sequence between two tasks, if they are performed by the same cranes k. And the next group of variables is the time allocation variables. It will handle the actual operation time of each task, so and calculate the real mix span. So the variable z, it can be used to indicate the operation sequence between two tasks, even the two tasks are assigned to different cranes. Correspondingly, the constraints can be categorized into two groups. The first group is task assignment sequencing, like including the constraints like the unique crane allocation for each task, and And the second group is the time allocation. The time allocation constraints. It is used to consider the collisions between among the cranes using the a very significant parameter delta IGUV. It means that if the two tasks, if task I is assigned to crane U, if G is assigned to crane V, then the parameter delta will tell us that if these two assignments can be operated simultaneously or not. If not, there is a minimal time to elapse between the processing of these two tasks. Okay, inspired by the Sampile, they work by Sampile and so on. We separate these constraints into two problems. One problem is the sequencing master problem. It is related to the task assignment and the task sequencing. And the other part is categorized into the time allocation subproblem. It mainly considers the allocation of to calculate the real completion time of each task and also the cranes. So in the combinatorial Benders approach, we proposed we first solve the task assignment and sequencing, the sequencing master problem, and we obtain the values of the variable x and y, and pass that to the subproblem, and then solve the time allocation subproblem. If we found the problem is infeasible or suboptimal, we will derive a combinatorial cars and add that in back to the master problem. So this will be solved iteratively, and then it will stop. It will be terminated if the lower bound is equal to the upper. The master problem. The master problem will provide the lower bound since it is a reduction of the whole problem, and the subproblem will provide the upper bound. So the termination of the algorithm is lower bound is equal to upper bound. So let me see the solution of the sequencing master problem. In the master problem, we only consider the operating sequences of each key crane. So actually the sequence is independent from each other. So in the master problem, we ignore the collisions between key cranes and also the task precedence if the two tasks are assigned to different key cranes. So this will result in infeasibility and suboptimality. You can see the three examples in the bottom. The first is we can result in saboteurs, like the task 5 to 6, 7, and then back to 5, task 5. And second, the precedence violation. So you can see the key crane 1 first perform task 4 and then task 6. Since task 6 must be performed before task 7, and then you can see that the task 3 is now performed after task 4. This is violate the precedence relation 3, 4. So another is that the key crane collision between are not considered. So there will be inevitable waiting time because we cannot the key cranes cannot cross each other. So in the basic Benders approach, I just explained that the master problem will provide a very bad lower bound, and the cut is really loose. So you can see that um, you can see that in the set C, it involves the variables of x equals to 1 because the constraints of a unique Key-Crane allocation, we can only consider the variables that of x which equals to 1. So, but the number of the number of characters in the set C, it's n squared plus n, so it's a large number. And in each iteration, only one variable in set C, if it changes, then a new solution will be resulted, and it can be the new solution of the next iteration. So the cart is really loose. So our focus is the first we propose valid inequality to improve the solving of the master problem, and then we will try to propose some tighter combinatorial cards, and also selected multiple cask generation strategy to improve the cask generation, and so as to accelerate the convergence of the algorithm. And the last strategy is the time allocation heuristics to improve the upper bound. In the strategy of tighter combinatorial cask generation, it mainly includes three strategies. The first is no good cut. It is associated with the suboptimal solutions. And the other one is the infeasible combinatorial cost. It is associated with the infeasible solution. Actually, our idea is to find the subsets of the C set, and then we can derive efficient combinatorial cards. Sorry. So for the first strategy, valid inequalities, we propose the first one is called lower bound inequality. The basic idea is that the total time that a given Key-Crane will stay on the left side of a given bay should be no less than that of its right adjacent Key-Crane. So for these two Key-Cranes, the compare baseline is the mixed one. For example, if the current solution indicated that all the operations will be terminated like within 10 time units, then in the period there of 10 time units, the Key-Crane one, let's indicate this the leftmost QC, let's indicate let's see QC1. It's staying time like in this bay will be no less than the total staying time of Key-Crane 2 staying in this bay. So this is a basic observation. We can derive the lower bound inequalities. It's really similar to the unidirectional of Key-Crane scheduling problem formulation, but we ignore we relax the precedence constraints. It works really good actually. And the interesting part is that when we add these inequalities into the master problem, the solving time is accelerated. The master problem became easier to be solved. So the second inequality is the moving inequalities. It mainly focus on the case of involving the subtools, like in this figure. So the main idea is the QC moving time from task 0 to T. Oh, sorry. Task 0 is virtual task indicate the very starting task of each query. And task T is the virtual task stating the ending task of each query. So you can see that the total moving time here from task 0 to task T is only it's 0, actually 0 moving time. So this is not right? So actually, you can see the task 5, 6, and 7, they are also assigned to the Quay Crane 1. So actually, the moving time should be no less than like the 1, 2, 3, 4, right? 4 periods. So the minimum here Quay Crane moving time can be calculated by the Bay range. So this is the basic idea. The last valid inequality is about the precedence-based mixed span inequality. Let us see the example in this figure. Like see the root of the Quay Crane 2. It first start from 0 and then 4, 7, 8, 9, 10. Let's see. Let's suppose there is a precedence relationship between task 3 and task 4. Let's consider the case that the task 3, the operation time of task 3 is really big. In that case, that the Quay Crane 2 should wait until task 3 is completed, then it can start to operate to perform task 4, right? So in this case, we can propose a new inequality to calculate the minimum mixed span. So you can see this is how the inequality works. So next part is the no good cuts. What we consider is that let us first introduce the two sets. The first set SI0 means that the tasks performed before the task I, and set SGT means that all the tasks performed after task G, and we indicate the query that's assigned to perform task I is KI, and the KJ means the key queries that operate the task G. So you can see that what if the task I and G, they cannot be performed simultaneously, like due to the key crane collation constraints. And so in this case, either the tasks in set Si0 and the task I is performed before task G, or the task G is performed before task I, right? They have to determine the operation sequence between task I and task G. So in this case, we have to, if this condition is satisfied, this means that the operation time of task set of the tasks in set Si0 past task I and the task G and the task and set tasks in set SJT it is bigger than the upper one, or the due living time of the Crane KG, then this the operation sequence that task I is performed before task J, this operation sequence is not optimal for sure. So for the second case, that if we see that the second case is that J is performed before task I, we also have similar condition. Then all the operation sequences of task Crane Ki and Kj are suboptimal, so we can derive the corresponding card to eliminate this suboptimal solution. So this card involves two sets. That's SI-link, SIT, SI0, sorry, SI0, SIT, SJ0, and SJT. So consider further considering that sorry, another note should be noted, that is this card works no matter in which order the tasks in SI-link and the task SJT are processed. You see that we in this expression, no matter they are processed, but as long as the number of these variables equals to the number of the sets of the tasks in this set, this sequence are all suboptimal. So consider a further case that if task I and J satisfy the precedence relationship, then only the task, only the set SI-link and SI0 and SJT is involved, right? So a new lifted class can be proposed. So actually, this is not the end. Consider a further case that what if that if there is a lot of tasks that should be operated before task J due to the task precedence relationship. If we summarize if the sum up all the operation time of the tasks should be performed before task J, we found that this is this summed operation time is larger than the operation time of the tasks in set SI0. We can see that so this sequence from task G to task T, this half sequence is really is in fact suboptimal. So we derived a new card involving the set SJT only. So this is actually the card lifting routine. So let's consider the another case that what if there is no precedence relationship between task and J? Is there any way to lift the basic no good card? Yes. In this case, we only consider if there is a Quay Crane collision relationship force that task I should be performed before task J. Then we can derive a lifted card. You can see in this card that all the tasks in SJ-link and they cannot be performed simultaneously before cannot be operated simultaneously with task G.
Defeng, we lost you. It's okay now. Okay, it's okay.
Okay. Sorry for the bad network. Okay, so in this case, we can we can draw the conclusion that the task I should be processed after task G. So a new lifted cards can be proposed. Actually, there are a lot of other cases we can derive similar cards. For the
I think we lost you.
For the task precedence
I think maybe you can switch off camera, so switch off video so that we have better throughput. We don't hear you. Defeng, do you hear me? Defeng, please, do you hear me? Defeng. It's lost. Yeah, Defeng, do you hear me?
Yeah, I'm really sorry for the bad network.
No worries. Maybe you can switch off video, which maybe
Okay.
is charging the network, and we just will hear you. Just share the slides, please, again. Yeah, we see it. You can go on, right?
Okay. Sorry for the bad network. I will continue my explanation. So I'm not sure which part I stop connection. So I will quickly back to the pages. This is a lift card considering task precedence, and this is the lifted card if there is no precedence relationship. And this is the cut to eliminate subtours. This is the cut to eliminate the precedence violation, like from task 4 to 6 and task sequence from 7 to 3.
Hello.
Yeah. Actually, the last infeasibility card is the safe margin violation elimination. So you can see the examples in the right side. On the right side, it is if a queen that operates task 1 to 4, 5, and back to task 3, you can see in the B, the task 2 is if a task 2 is assigned to a different sequence, that's because these two bits are within the safe margin, like if the safe margin equals 1. So actually when the key crane, let's say key crane 1 operates in bay B and B plus 1, then task 2 there is no time for there is no time for other key cranes to operate task 2 because of the task precedence 2, 3, right? So a second case is that if the key crane 1 operates task 1, 4, 5, and then terminate, so then the task 2 and 3 cannot be performed by any key crane because the key crane 1 is stop at the bay the bay B plus 1. So other key currents, they cannot enter into this bay B because of the safe margin of requirement of key current 1. So we can derive corresponding cards to eliminate this kind of safe margin violation. So the last one, the last card generation strategy is the selected multiple cards. The basic idea is that we can change the elements in the set SI0 and SI0 and SJT. So let's take the subset for example. If let us see that capital S, yes, a hat. I forgot the word. Sorry. Let me see the hat S. The set hat S is hat S I0 and hat S JT be the subsets of SI0 and SIJT. If we satisfy this condition, that the operation times of the tasks in as hat as I0, if we sum all the operation time, then we found that it is bigger than the upper bound, then actually the operation sequence that from task 0 and all the tasks in task hat SI0 and then task I and then task G and then all the tasks in in the set as hat as JT. This sequence is not cannot be optimal because the actually operation time will definitely bigger than the upper bound. So actually, this can provide us idea to generate selected cards because that we can actually in each iteration when we solve the master problem, we can use neighborhood search to generate more solutions of the master problem. But if we generate the combinatorial cards for each the new solution, then the number of cards will be grow rapidly. So the master problem will probably be hard to solve. But if we derive a set of subset-based cards, if each of the subset-based card can covers as many suboptimal solutions as possible, then we can generate limited subset cards, and the master problem will be easier to solve, but the cards will also be really in good quality. So this is our basic idea, but this strategy is still an ongoing work. We are trying different strategies to select the cards. So the basic strategy we adopted is that we generate a lot of new solutions by neighborhood search, and we record the values of X. Then we select the we treat the summarized X values as the weight, and we select all the linkage from task n to task like variable xijk. If the weight is bigger, then we will treat it like reserve the task energy in the subset, and until this condition is not satisfied. So this is it's a easy strategy, but there is a possibility to propose other strategies that might be more efficient. So the last strategy is time allocation heuristics for improving upper bound. So actually, in the former no good class, we rely on the upper bound, right? So the upper bound, the quality of upper bound is really it really matters in the cut generation. So we propose some time allocation heuristic for improving the upper bound. The basic idea is that since the assignment determines a sequence in the unidirectional and bidirectional Quay Crane scheduling problem, so we can check if the assignment, this assignment means the variable y, like variable yik means if task I is assigned to Quay Crane k, if this assignment meets the requirement of unidirectional bidirectional Quay Crane scheduling, if yes, then solve the unidirectional and the bidirectional Quay Crane scheduling problem under given task assignments, and this will probably update upper bound. And we do some computational experiments on the benchmark instances, like in the benchmark instance provided by Cayman Park. There is like 9 groups of instances in the benchmark instance of Meso and Burvis, and it is 7 group of instances. Each of them, they are different in either in the scale, like the number of tasks, number of bits, and number of Quay Cranes, or some parameters like the precedence densities. So the results show the good performance of our algorithms. Let me explain the different versions of algorithm. The first is the bidirectional Benders approach. The Benders approach method for the bidirectional Quay Crane scheduling problem, and the SBD means there's the Benders approach, Benders decomposition approach proposed by Sampaio and so on. Their method is first state-of-art method, and the best exact algorithm we know so far. And the first approach we propose is that the combined Benders decomposition version 1 is that is the SBD algorithm plus the valid inequalities, and the final algorithm is the complete version of the Benders approach we proposed. You can see the number of instances often solved within our in our algorithm. They will be 385 instances solved to optimal, and for out of total 490 instances. For other, like the Benders approach of SBD, there are only 37. So that means that show the efficiency of the strategies we proposed. So that's more that's all my work, and actually there is a lot of future work. the first work is that we can keep generating the formulation algorithm to cover more variants. So the second work is that we have to propose more efficient strategies for selecting the multiple cards. And we also can consider the robust method for uncertain Quay Crane scheduling problem. So that's all. Thanks for attention.
Okay, thank you very much. And now the questions. Anybody wants to ask a question? If not, then I will ask the first one. How far are you from a real application? So are there any constraints that you have neglected, or do you have any notion on how it is really happening in real port, and what could be the differences, right?
Actually, our work is applied in the big container terminal like Tianjin port.
Okay, so it's already applied in the terminal, right?
Yes,
Okay,
but not the
congratulations.
complete version. They are really concerned with the computational time, and actually they want to know that's how like the gap between the near optimal solution and the lower bound. So in our method, we can quickly give this analysis this bound and give them a very good solution. Yeah.
Okay, thank you. Any other question? Please ask something if you are close to the subject. If not, I would like to mention that there was already one talk in our seminar on conflict-free crane scheduling in seaports by Erwin Pesch, right? So we have already a second talk on this subject. And last call for questions. If nobody is interested to ask, then I thank to the speaker. Thank you. It was a really interesting industrial problem applied in practice, which is very nice. And let me mention the next talk, which will be given in 4 weeks from now. It will be given by Daniel Vigo. He's from neighboring community on vehicle routing, but I think he has a very nice subject to speak about. So he will speak about large-scale problems in vehicle routing. And I apologize that it will be in 4 weeks from now, but one of the speakers was unable to give the talk in 2 weeks. So if everything works well, later on we will proceed with 2 weeks distance in our seminar, right? So once more, in 4 weeks we will have possibility to hear Daniel Vigo from CIRI ICT from Italy, and that's it. Thank you very much for being with me at this occasion of scheduling seminar, and I hope to meet you in 4 weeks. Thank you. Bye-bye.
Thank you. Bye.
Bye-bye.
Thank you.